Hello everyone. In this video, I am going to talk about Chapter 15, Section 15.4. We are going to understand and analyze the mechanical impact. We're going to look at a lot of collisions together and then analyze the motion of the body undergoing a collision in both central and oblique case of impact. Typical problem, a lot of the standard classic problem will be um, balls hitting each other. Impact occurs when two bodies collide during a very short period of time. This is causing large impulsive force to exert between the bodies. Common examples are hammer striking a nail, or if you play baseball, when the baseball bat striking a ball. The line of impact is a line through the mass centers of the colliding particles. In general, we have two types of impact. The central impact occurs when the direction of motion of the two colliding particles are along the line of impact, and oblique impact occurs when the direction of motion of one or both of the particles is at an angle. So they're coming in at an angle, or they are coming in um, at a line. Central impact, first off, happens when the velocity of two objects along the line of impact. Recall that the line of impact is a line through the particle's mass centers. Once the particle contact, they may deform if they are not rigid. In any case, energy is transferred between the two particles. There are two primary equations we're going to be using to solve the impact problems. Textbook show you more details. Basically, first equation says conservation of linear momentum. Initial linear momentum for all the particles together, particle A, particle B initial together, equals the sum of linear momentum of all the particle A, particle B after the collision. Before collision, total linear momentum equals the total linear momentum after the collision. This equation usually has two unknowns. That means we need one additional equation. And this one additional equation will be principle of impulse and moment. Um, this usually refers to the coefficient of restitution, or the value of E here. Coefficient of restitution is defined as the ratio of the particle's relative separation velocity after the impact divided by particle's relative approach velocity before the impact. So the velocity difference before the numerator goes to the difference of the velocity before the after the impact. After impact goes on the numerator, before the impact goes on the denominator. So coefficient of restitution is an indicator of the energy loss during the impact. Put it in the equation in the fraction form, looks like this. And if we know the value of E, the relation provides a second equation necessary to solve our problem. Special cases, under the condition that elastic impact E equals 1, it's a perfectly elastic collision. It means that no energy is lost, and the relative separation velocity equals the relative approach velocity of the particles. In practical situations, this condition cannot be achieved. It doesn't really happen. Realistically, this does not happen. But sometimes we assume this is the case to simplify our calculation. If you have E value equal to 0, that will be the plastic impact. In this case, relative separation velocity is 0. That means after the collision, two particles stick together and move with a common velocity after the impact. And down here shows some typical values of the E. Depends on the material, the steel on steel, wood on wood, glass on glass, etc. Once the particle velocity before and after collision have been determined, the energy lost during the collision can be calculated on the basis of difference of a particle kinetic energy. So we put the kinetic energy before and after the collision together, we can calculate the energy loss. And during the collision, some of the particle initial kinetic energy will be lost in the form of heat, sound, or due to the localized deformation. In a plastic collision, E equals 0, the energy loss is a maximum, although the energy of the combined masses does not necessarily go to 0. Oblique impact, did they come at an angle? One or both of the particle motion is at an angle. So typically there will be four unknowns. Since velocity are vectors, right? We need the magnitude and the direction. So that means we will have four unknowns of the final velocity. The four equations required to solve them will be we're going to use four equations that will be conservation of momentum and the coefficient of restitution equation are applied along the line of impact on the x-axis. I will show you some examples in a little bit. Keep in mind that momentum of each particle is conserved in the direction perpendicular to the line of impact on the y-axis. So, in other words, coming in, right, vertically on the vertical direction, there's no change on the velocity. My particle A before the impact, velocity before the impact, after the impact should be the same. Same thing as your B. This particle vertical component of the velocity before and after the impact will be the same. So in most impact problem, initial velocity and the coefficient of restitution are given to you. We're going to try to determine the final velocity. We're going to define the xy axis. Typically, the x-axis is defined as along the line of impact, and the y-axis is the plane of impact perpendicular to the x-axis. For both center and oblique impact problems, the following equation apply along the line of impact. So overall, we have total initial momentum equals total overall final momentum, and we also have an equation for the E. For oblique impact problems, the following equation are also required applied to the perpendicular only, as we taught from the previous slide. Perpendicular velocity, perpendicular component does not change before and after the impact. Okay, what changes is the horizontal. So now this one, so don't keep in mind that be careful with the direction. Even though on the previous slide we keep on talking about the y component of the velocity does not change, in this problem it's the x does not change. Wait, hold on. This one does, yeah, x does change. The y does not change. Yeah, there we go. Be careful with the direction is what I'm trying to say. Sometimes when you hit the ground, hitting the wall, be careful with the direction. So we know the ball strike the smooth wall with a velocity VB. We know the velocity coming in with a 30-degree angle. We also know the coefficient of restitution between the ball and the wall is E equals 0.75. We're looking for the velocity of the ball just after the impact. Now, we know on the y direction, the momentum of the ball conserved. VB1 sine 30, VB2 sine theta, we don't know that angle. So we can get the VB2 sine theta equals 10 meters per second based on this equation. We don't know the angle, but we know the y value should be the same before and after the impact. Plug in the equation for the coefficient of restitution. We get an expression for VB2 cosine theta. So in other words, the x component. Using this, we get the expression for x component of the VB. Now putting this together, we have the y component of the VB2. We get the x component of the VB2. We can figure out what is the VB overall. And using that, we can also understand, we can calculate the theta, angle theta, for us to figure out. If I know the x value, I know the y value, I know what is the angle between them. Okay. Group problem. We have a tennis ball is served horizontally 7.5 feet above the ground and strikes the smooth ground at B. It is known that E equals 0.8. We're looking for the VA and VB, the speed of ball just after it strikes the court. So we know that once the ball comes out with the initial horizontal velocity VA, it's going to be projectile motion. Projectile motion vertically, it's going to be free fall. So we're using the calculation here. This part of calculation is that we know the height is 7.5. We know that along the vertical direction, it's free fall. And we can calculate how much time does it take from point A to point B. Once we know the time, we know that this time is being shared by the horizontal direction and the vertical direction. That means vertically, along the vertical direction, initially vertical direction of velocity is 0. If I know the time, I can figure out the velocity on the vertical direction. Okay. And then using this total distance, the horizontal distance is 20 feet. And I know it took, the range is 20 feet. And I know it took 0.6825 seconds. I know how much time it takes. It can help. I can use that to calculate the horizontal velocity. Okay, so that now based on this two, I know the vertical velocity, vertical component of velocity. I also know the horizontal component of velocity. Putting these two together, that will give me the velocity overall. But hold that thought. We will also use the coefficient of restitution in the y direction to determine the velocity of the ball after the rebound. So this velocity vertical 21.98. This velocity vertical is the vertical velocity before, vertical component of the velocity before it hit the ground. And then we can use this equation for the E, coefficient of restitution, to calculate the velocity vertical component after it leaves the ground, the moment after. Now with the B initial, B after, we can we know the B after. We hold on. We know the B after, and we know that we know the by after, a vertical component of the B after, and we know the bx after as well. Why is that? Horizontally, the bx, the x does not change. So 29.3 is the horizontal velocity before we strike the floor, and it's the same after we leave the floor. Horizontal component of the velocity does not change. So we're using this number for the after horizontal component, and this will be our after vertical component. Put that together, that will give me the velocity overall. And you use tangent inverse to figure out the angle leaving the ground. Okay, that's all I want to share with you in this video. Hope you find this helpful, and thank you for watching.